Hi guys, it's your guy Olumide. Today we'll be solving another one of the most commonly asked tech interview question, the bipartite graph validation problem. It's a DSA problem that's commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. The problem statement states that given an undirected graph, determine if it's bipartite. A graph is bipartite if the node can be colored in one of two colors so that no two adjacent nodes are the same color. The input is presented as an adjacency list where graph_i is a list of all nodes adjacent to I. And we're giving this example right here, and this is the input. This is the input, and the input is actually a graph. Is actually a list of lists, which we call the adjacency list, because it's a list that actually relates a index or a node to its neighbor. So because it's a list of lists, so every list that is contained there actually represents a neighbor to the index, to enable to its index. For now, like now, this particular list 1,4 corresponds to the neighbor of the index 0, while this particular list 0,2 corresponds to the neighbor of index 1, which corresponds to node 1, right? So, and that's what we can see here. Look at it right here. This 1,4 now a neighbor of index 0 that corresponds to node 0. Look at node 0, and this is 1,4, 1 year, 4 years, so they are both neighbors of node 0. Similarly, for this 0,2 now, we can see that they are neighbors of the node 1, and similarly this list 1 is just a neighbor of node 2, so which is just one neighbor. So, and this is how it goes. So this graph actually, this list can help us develop this graph, right? Because it actually corresponds to an index which represents the node in the graph and their corresponding neighbors. So now the output is true because this graph, this structure is actually bipartite, because no matter how we always we have achieved to color the nodes in the graph such that no two adjacent nodes share the same color. Look at this adjacent node and this adjacent node, they share different colors, similarly to this and this and this and this, and all of them share different unique color every adjacent node, where the color blue, this color represents blue and this represents orange. Before we dive to solve the problem, let's first consider what a bipartite graph is and what it looks like. A graph is bipartite if the nodes in the graph, if each of these nodes could be divided into two distinct sets such that the edges actually runs between nodes of different sets, right? So it's actually bipartite if we can rearrange the node in that particular graph such that the connection between these two distinct or two adjacent nodes, consider say node 0 and node 1, or node 0 and node 4, or node 4 and node 3. So in such a way that this connection, these edges actually crosses between the different sets and not across the same set or nodes within the same set. So that's when we say it is actually bipartite. Consider this one now. You see that this is bipartite because the edges actually crosses between nodes between the different sets, right? Look at node between 0 and 1. Here there's a connection, just like we can see it on this part. So and we are able to divide the nodes into two different sets, whereby the edges actually runs between nodes of different sets and not between nodes of similar sets. So in a situation whereby the edges actually run between nodes of the same set, or a situation whereby there's no way we want to place and we want to set nodes into two distinct sets without the node crossing nodes without the edges crossing nodes within the same set, definitely it is not bipartite. Consider this particular example now. It's actually a cyclic graph because it forms a cycle, a loop, right? So look at it now. When we try to divide it into two distinct sets now, whereby 0 connects to 1 to 4, so we believe 1 to 4 should be on the other side, so that there won't be any form of edges crossing the same these nodes of the same set, right? So we set as 0 and 0 connect to 1 right here, and then 0 also connect to 4, just like we have it here. And similarly, this is undirected, right? We call it undirected graph, meaning that just the same way 0 is connecting to 4, 4 is similarly connecting to 0, just the same way 1 is connecting to 2, 2 is similarly connecting to 1. So but we can say that on placing 3, 3 is actually connected to both 4 and 2. So and there's no way when I place it that it is not going to break that rule of bipartite graph. Why? Because it will end up having an edge between nodes within the same set, right? So look at it now. When we place our 3 right here, it still connects with 2. Why? Because that's connects with 2 and 4. And at the same time, when we try to shift it to the other side, it still connects with 4. So there's still this edge that is being shared by nodes of the same set. So there's no way this can be a bipartite graph. Now, to determine if a graph is bipartite, we can use the concept of graph coloring, whereby we try to color one set, or a set of nodes with a particular color, and the second set of nodes with another particular color, while ensuring that no adjacent node share the same color. So no adjacent node for now. Like now, for this particularly bipartite, you see that no adjacent set, no adjacent nodes share the same color. These are adjacent node. So we try to position the set and the node in such a way that one set is gonna share a particular color, another set is gonna share a particular color, and there will be no relationship, no edge joining between nodes of the same set. So therefore, no two sets, or no two connecting nodes or edge connecting nodes is gonna share the same color. So look at, in this situation, you see that this is a perfect example whereby no two connecting nodes, these are connecting node here, these are connecting, any node that any two nodes that have an edge connecting them are actually connecting node. And for a bipartite graph, for them to satisfy the bipartite condition, definitely they must not share the same color when they share the same edge, when they are connected together. Now let's explore this idea to try to check if this particular graph is bipartite or not. We are going to be using two colors, the color blue and the color orange. So for coloring, why was by default, they are not colored by default, but subsequently we're going to be coloring the node blue and orange. One potential strategy that we can use is that for each node that we color, we are gonna color all its neighbor the opposite color, right? So meaning that if we color our this node 0 red, for instance, then we will color its neighbors as blue, because that is actually the principle we are following, that the adjacent nodes needs to have, they must, no two adjacent nodes must have the same color, right? So let's go on with that. So first of all, we are gonna use our DFS search method to traverse this graph. Don't forget, we are gonna be traversing the graph. Why? Because we really need to reach the neighbors, and then from the neighbors reach their own neighbors as well. So we'll be traversing the graph, and we'll be using the DFS method, so we should understand very soon. So let's say we traverse, we color this particular node. We start here and we color the node as orange, right? Fine. Meaning that now we have to color its two adjacent node as blue. So first of all, let's color the first adjacent node, this one, as blue. So right now we are at this particular node now, and we colored it as blue. So now this particular node, having been colored as blue, we have to color its adjacent node as red again, right? So since this one, node 0, have been colored, let's go on to color its node 2 as red, right? So fine. Now since node 2 have been colored as red, so we have to color the adjacent nodes to nodes 2 as blue, right? So and that will cause us to color node 3 as blue, since node 1 has been visited already, so and it's already blue. Fine. So now since node 3 have been colored now as blue, then that means that its adjacent node needs to be colored as red. So and that's what leads us here, that we color this particular node now, node 4, as red. But one thing you realize is that now node 4 and node 0 are adjacent nodes, and they now share the same color, which signifies that this particular graph is actually by portrait. So and one thing, well, you might be like, how sure are we that this strategy actually work? Well, if you remember, right from the beginning, we have been coloring the nodes with adjacent alternative colors, right? If we color this one as red, we color its neighbor as blue. So actually there is no different other way to do it, to make node 0 and node 4 different color, right? Why? Because we'll be coloring them alternatively all the way. So even if we decide to start with colored blue, node 4 will also end up with colored blue as node 0. So it's actually a very good strategy to use. So and what about, let's say, how do we handle multiple component now? So don't forget, this component actually is not multiple. I mean, this graph, it actually form a graph, a single graph, right? But what if we have a multiple component graph like this? So don't forget that this graph is given to us as an adjacency list. So what just differs is that there is no connection between this particular adjacency node and this particular adjacency node. So if I'm to write down the relationship now, let's just write down adjacency list for all this particular graph with 2 components, right? So to write it down, we just have node 0 having node 1 and node 2 as neighbors, right? So and node 1 also having node 0 and node 3 as neighbors, so 0 and 3. So and then node 2 having node 0 and node 3 as neighbors, so node 0 and node 3. And then node 4, okay, that's okay, this node 0, node 1, node 2. Now let's talk about node 3. Node 3, we have node 1 and node 2 as neighbors, right? So fine. Now you see that node 4 also have node 5 as neighbors, and node 5 has node 4 as neighbors. So this is simply this graph that you can see. This is the adjacency list. So it's actually a valid graph, but having multiple components. Now how do we solve it? How we solve it is that after navigating, we just try to do the same thing for any graph that has not been colored, meaning that when we start from node 0 and we proceed to paint node 1 on node 2, just like we have it here, this is DFS of 0. When we call DFS on it, when we try to perform DFS on it so that we can reach its neighbor, we are able to paint its neighbor, right? Then calling DFS on 1 as well, we can able to paint its neighbor. So and when we paint the neighbor all around like that, we are going to proceed to try to check if there is still any node that is not colored. Then we will find out that this one has not been colored, and then we'll paint it. And now we can do that is by actually iterating through each node. So having starting from here and calling DFS on here to get every other part colored, because when we call DFS on this one, it gets this color. Then recursively we are able to get this one neighbor to colored. I mean this particular one neighbor color, and recursively we get this neighbor colored, and that's how we are done with it, right? So don't forget that the DFS is initially called on 0 on node 0 to get everything colored. So we are still gonna go back to call it on node 1, on node 2, on node 3, and node 4 and node 5. But the difference there is that node 1 have been colored already, so we won't do anything. Similarly node 2, node 3, but you will now find out that node 4 have not been colored. So at that point we are gonna color node 4, and it's gonna in turn color node 5. So that's how we handle multiple components. So this is how we'll be solving this problem. And then to represent the red and blue color, we're gonna be using 1 as red and -1 as blue. So and that means that at this particular the first node we're gonna color it red, then we'll proceed to, which means 1. So we're gonna set its color attribute to something like 1. So and then we're gonna proceed to its neighbor, so and set all its neighbor to 0. And then right from this neighbor here, before we get to the next neighbor, we are gonna try to go into their neighbor's neighbor, because we want to just make sure that it continues like that. That's what we call DFS. It's gonna recursively do that, going in depth. So we are going to the code implementation now. follow along. Alright, let's go into the code implementation for the bipartite graph validation problem. We're going to be calling the function bipartite graph validation, and don't forget it's going to be collecting a graph, so which is actually we call it the adjacency list that will help us to structure the graph, right? So, and it's actually a list of integers which actually represent nodes and their neighbors, right? So here we'll be returning a boolean, I think, yeah, because we just want to check whether true or false if it's a bipartite graph. So we're gonna be having this graph structure here, and we are gonna be printing it here. So this is actually the graph structure that is given to us in the problem statement, right? And don't forget that each of them actually represent the neighbors of that particular index. So 1,4 actually represent the neighbors of index 0, and 0,2 similarly represent the index of neighbor 1, and that's how it goes like that. So first, let's define a hash map, right? This hash map is gonna help us to set the each node as unvisited. What I mean by that is that don't forget that in this graph each index corresponds to a node, and the element or the list at that index corresponds to the neighbors of that node. So right from time this node is not visited, right? What I mean is that it is not colored, whether red or orange, whether -1 or +1, it is not colored. So because we have not yet traversed it, so we're gonna be setting them to 0. So we are gonna call it node slash n. So let's set them to 0. So for node in length of graph, so let's set it to range of length of graph, right? So you might be wondering what I'm doing right here is I'm just trying to create a dictionary of these indices. So you see that I use range of length of graph, meaning that this index is why, because this indices of the graph corresponds to node. So this corresponds to node 0, then node 1, then node 2, node 3, node 4, right? So, and then I'm just trying to create a dictionary of node to key, node to value, and the value is set to 0 right from time. So subsequently it will be populated with either 1 or -1, but right now it is uncolored because we have not yet started coloring it. So fine, now let's iterate through the graph to get them colored, to get each node colored, or let me say to get each node that have not been colored, even though we know right from time at the beginning none of them is colored. We have them all set to 0 right in the hash map. So for node in graph in, let's say, range, so each node in range of length of graph, right? So for each of this node we wanna get it colored if it is not colored. So if not hash map of node, or let me say if hash map of node is equals to 0, right? To see if it is not colored, then what we want to do is that we want to color it hash map of node. So we're going to be coloring it as red at first, which is actually 1, right? So we're going to be setting it to 1, so meaning that that particular node has been colored. Now what remains is actually to go on to actually color its neighboring node. So we're going to pass in that node to the DFS. We're going to pass in hash map of node, right? So which actually corresponds to the color. So don't forget that the color that we color the current node is going to determine the color we're going to color its neighbor. So if we color the current node 1, we definitely will be coloring its neighbor -1. So I'm going to be passing in graph to hit yeah, and let's pass in the hash map as well, right? So now let's go collect the call the function DFS. So it's gonna take in the node, which is actually an integer node, so that represents node 0 or node 1 or node 2 or node 3 or node 4. So and also we have the hash map, which is actually a dict object that represents the nodes to their color a node to color ratio or key value pair, right? So also we are defining the graph, which is actually a list of integers, and also we are defining the hash map, which is a dictionary, right? Okay, I think I talked about the hash map, but the hash map is supposed to be here, right? So okay, here is hash map of node, so it's just actually telling us about the color, right? So it's talking about the color is an integer. So hash map of node is telling us the color of that node that we are trying to, so we are trying to change this neighbor to the opposite color, right? So and then now let's try to change the neighbor of it to the opposite color, and now we can do it is by saying that for neighbor in graph of node, so don't forget that graph of I corresponds to the node of that node I, so graph of node corresponds to the neighbor of that node, right? So for neighbor in graph of I, so first of all we want to check if they have the same color. If graph how we can check if they are the same color, it is actually hidden in our hash map. Our hash map is gonna keep track of whether they have the same color or not. So hash map of neighbor, so don't forget neighbor is just like a neighboring node to that particular node. So if the neighbor has a same has the same color as the current node color, meaning that if the current node and its neighbor or any of its neighbor has the same color, then there is a problem and we should return false. So it means that it is not a bipartite, actually it's not a bipartite graph, because a neighbor and two adjacent cells or two adjacent nodes actually have the same color. So that is if the neighbor has the same color as this one. Don't forget, so for the neighbor to have the same color, definitely the neighbor have been colored, right? So the color now appear to coincide with the two adjacent neighbors, right? So but in a situation whereby hash map of neighbor, that is if the color of the neighbor is just 0, definitely don't forget that we are calling this DFS function to color the adjacent, or let me say the neighbors of that current node to the opposite color. Had it been the color is 1, now it's gonna color it to -1. If it is -1, it's gonna get its color to 1, right? So but if the color is still 0, meaning that it has not even been colored at all, then what we wanna do is just color wanna color it to the opposite color. Hash map of neighbor, so we just change the color to minus color, right? And I believe you know what that means. It means that okay, if the color is 1, it changes it sets the color of this particular neighbor to -1, while if the color is -1, it's gonna set the color of this particular neighbor, that is the adjacent neighbor, to 1. So and after that, now we have to go deep into this particular neighbor. Now we are gonna call the DFS function on it, so that we can actually color its neighbor, this particular neighbor's neighbor, right? So I'm doing that. I'm just gonna send in the neighbor, right? We're gonna send in hash map of neighbor, right? So where I'm saying hash map of neighbor, if I don't forget, we have updated the hash map of the neighbor to -color, so we can easily just call hash map of neighbor now, so that it's gonna set its neighbors to -color as well. Don't forget, it's gonna correct it as -color right here. So doing that, now we're gonna pass in the graph as well, and we're gonna pass in hash map as well. So hash map as well. So now this actually means that, so you will see that one thing I did not put now is that I did not consider a situation whereby the color is actually -color. Fine, I consider when a situation whereby the color of the neighbor is the same as the color of the the adjacent node, right? So in situation like that, I return false because no two adjacent nodes or neighbor should share the same color. And I consider a situation whereby the neighbor is actually neutral, it doesn't have a color yet. But you notice that I don't consider a situation whereby the neighbor has an opposite color, that is minus color. And why is because such a neighbor has been visited already, it has been given a color, right, and the color does not correspond to this particular neighboring or adjacent cell or node. So because of that, we don't need to go into it again and to change its color or to call DFS on it, because for a node to be colored, definitely it has been sent to this DFS function. It has been, and it has a neighbor colored as well. So we don't have to consider a situation whereby the cell or the neighbor have been colored and the color does not rhyme with its adjacent cell. We just leave it like that. All we want to consider is when the neighbor have not been colored at all, or when the color is the same, which in that case, whereby the color is the same, we return false, right? So now if we can just consider the neighbor of any particular node and then we successfully loop out of each of the neighbor, give them their color without returning false, definitely we should be able to return true, right? Meaning that that particular node and its neighbor are in good terms, right? So and we return true. So looking at this now, you see that the return of this DFS is actually a true or false. So therefore it means that right here we can just try to check if DFS actually returns false. So if not DFS, mean that if it returns false, what we now do is that we want to return false, meaning that imagine a situation whereby two neighbors have the same color and then it return false here. Definitely we want to return false throughout. If any two neighbors can have the same color, then the graph is not a valid bipartite graph, so we want to return false. But if it can loop through each and every neighbor and none of them return false, then we can easily and legally return true, right? So and that's how to solve this problem. Let's run it and let's see. Oh, I think we have a true printed, but let's see. Yeah, we have a true printed right here, and it's actually returned true. So this is how to solve this problem, and I really hope you understand this. I really hope you understand it. Kindly do also subscribe to my YouTube channel if you have not, and follow me on my other social media platform. I give good updates on DSA problems and Leetcode problems, and those other interview patterns like behavioral patterns, system design and architecture, and other things like that, and tech updates. So subscribe and thank you.